Okay, so we're going to start with number 12, and we need to suppose that 100 milligrams of a material decayed to 70% of its original mass in 16 years, and we need to find the continuous decay rate in the formula y equals a times e to the kt. Okay, so we know a is our initial value, and so we know our formula is going to be of the form y equals 100 e to the kt, and so we just need to find what k is. We also know that after 16 years, we only have 70% of our material left. So I think we can write another equation that says 70% of 100 should be 70. 70 is going to equal 100 times e to the k, and then we're told that takes 16 years, so times 16. And now our task is to solve for k. So I think my first step is going to be divide by 100 on both sides. Okay. So then I have 0.7 equals e to the 16k. And then to get rid of the e, I'm going to take the natural log of both sides. So I'm going to have the natural log of 0.7 equals the natural log of e to the 16k, and now I'm able to take that exponent down, and we know that the natural log of 0.7 equals 16k times the natural log of e, but the natural log of e is just 1, so this will go to 1. All right, and so now we can go ahead and divide both sides by 16. So we know that k equals natural log of 0.7 over 16, and so when we punch that into our calculators, we will get a negative 0.0223. Okay, great. Okay, now we know our k value, so we can go ahead and plug it into our formula, and we should get that y equals, our initial value is 100, times e to the negative 0.0223 times t. Okay, next we're going to find a formula in the form y equals a times b to the t. Okay, so a is still going to be our initial value, so I'm going to go ahead and write 100 times b to the t, and we need that to be the same as 100 times e to the negative 0.0223t. Okay, so then we have 100 on both sides, so we can divide by 100 on both sides or just go ahead and get rid of it. We could say that b to the power of t equals e to the negative 0.0223t. Okay, and so if it's not already clear, I'm going to go ahead and rewrite this right-hand side as e to the negative 0.0223 to the power of t, and hopefully we can see that b should equal e to the negative 0.0223, which when we put that in our calculators, we get that b is approximately equal to 0.9779. Okay, so now if we were to put that in our formula, we know that y equals 100 times 0.9779 to the power of t. Okay, perfect. All right, and then now we need to find by what percentage the radioactive material is decreasing each year. And so we can use either formula for this, either from B or from C. I'm going to use the formula from C just because it's less buttons to push in the calculator, but we're going to use the same formula that we used for problem 11. So we'll take I'm going to take the interval between our initial value and then one year after. And so I'm going to plug this into my formula and do new minus old over old times 100. Okay, and so my new value here would be after 1 year. So I'll do 100 times 0.9779 minus our initial value, 100, all over 100, times 100. Okay, and then we'll stick that in our calculator, and that should give us negative 2.21% or a decrease by 2.21%. Okay, perfect. Okay, and now we need to fill in the blank. If we have f of t equals 8 times 0.649 to the t, and we have t increasing by 1 unit, then we need to find out how much the function should decrease by. So we're just going to use the same percent change formula, and I'm just going to do it from 1 unit to 0. So I'll do 8 times 0.649 to the power of 1 minus 8 times 0.649 to the power of 0, but this is just 8, of course, over 8.649 to the 0. So we have our new minus our old over our old value times 100. That should give us our percentage decrease, and that will give us negative 35.1% or a 35.1% decrease. Okay, perfect. Next, we'll look at 14, and we have f of t equals 80 times e to the negative 0.4t, where t is the time in years, and we need to find the continuous decay rate. Well, lucky for us, that's just going to be this k right here. So I'll have negative 0.4, and I'll want to convert this to a percentage, so I'll multiply it by 100, and I'll have negative 40% as my decay rate. Okay, and then for number 15, we need to find the percentage decrease for that same f of t function, 80 times e to the negative 0.4t. So I'll use that same percentage change formula, and I'll do the change from 1 year to our initial value of 80. So I'll do 80 times e to the negative 0.4 times 1, and then I'll look at our initial value, 80 times e to the negative 0.4 times 0, so a time frame of 1 year, over our initial value, 80 e to the negative 0.4 times 0, and all of that times 100 to get it as a percent, and then we'll plug that into our calculators and get negative 32.97%, or a 32.97% decrease each year. Okay, now we're going to look at 16. We have if the population increases by 10% in 1 year, then it will increase by 20% in 2 years. Okay, so let's consider maybe a population of just 1, and it's going to increase by 10% for 2 years. So let's go ahead and look at that. Okay. That'll give us 1.21. And so let's actually find our percentage increase and see if it's 20%. Maybe you can already see what the answer will be here. But we'll do 1.21 times our, 1.21 minus our initial value of 1, because that's a number out in front here, all over 1. And that will give us times 100 to get as a percent, and that will give us 21%. So no, this is false. It'll actually increase by 21% in 2 years. Okay, great. False. Okay, let's go ahead and take a look at 17. We need to know what is true about A, B, and K to produce this graph over here. So if we start at A, and we have A is greater than 0, B is greater than 1, and K is greater than 0, I think we should have a graph that looks something like this, just our regular kind of exponential function. Okay, and then if we go over to B, notice that this is the same as A, but we just have little a is less than 0. So if little a is less than 0, little a is negative. So this would correspond to a reflection across the x-axis. And I think that would produce exactly the graph that we see here. So our answer should be B. Okay, let's take a look at 18a. I notice I have some coefficients in front of the log, so I'll go ahead and rewrite that. I have 10 to the power of log of x cubed plus log of y squared. And then I notice I have two logs being added together, so I can go ahead and rewrite that as multiplication inside of the log. So I'll have 10 to the power of log x cubed y squared. Then I have, my log base isn't specified, so I go ahead and assume that it's a common log, or log base 10. And then I know that these two are effectively going to cancel each other out, and I'm just left with what's in the argument of my log, and I just have x cubed times y squared. And that's our answer. Next, we'll look at 18b. And again, we notice we have a coefficient of 5 in front of the second natural log, so we'll go ahead and rewrite that as an exponent. So I have e to the power of the natural log of square root of x minus the natural log of x to the power of 5. And then I have two logs being subtracted, two natural logs, and so I can go ahead and rewrite that as a division inside the argument of the natural log. So this will become e to the power of natural log of the square root of x over x to the power of 5. Similarly, my natural log is really log base e, so again, these are going to go away, and I'm just left with what's inside the argument of my natural log, and that is the square root of x over x to the power of 5, and I can rewrite this as x to the 1/2 divided by x to the power of 5. And knowing that 5 is really 10/2, we can subtract our exponents and get that this expression is really equal to x to the negative 9/2. And we're done. Okay, so now we'll look at number 20, and we are given the graph of log base 4 of x, and we want f of x to equal negative log base 4 of x plus 2. Okay, so first we need to get our new graph, f of x. So always with transformations work inside and then out. So x plus 2, that indicates we're going to shift everything to the left 2. And then the negative in the front indicates that we will reflect across our x-axis. So my asymptote on my original graph is at x equals 0, so now it should be at x equals negative 2. And then once I've flipped my graph, once I've shifted my graph and flipped it, it should look something like this. Okay. All right. So our domain, pretty clearly we can see that we go from negative 2 all the way to infinity. And then our range, we can see we're going to hit all real numbers, so it's going to be negative infinity to positive infinity. We can see that from the graph. We're hitting everything above the x-axis and everything below. Yeah. Okay, and then for 20b, we kind of already discussed this, but our asymptote has just shifted over from x equals 0. It shifted over left 2, so now it's at x equals negative 2. Okay, and then for d, as x approaches negative 2 from the right side, that's what the little plus means. So we'll look at what our function is doing as we approach from this side, and it looks like our function is going up to positive infinity when x approaches negative 2 from the right. And then as x approaches infinity, our f of x is approaching negative infinity. You can see it's kind of going down, down this way towards the negative infinities. Okay, great. Okay, and then we'll look at 21. For 21a, let's go ahead and start by taking the natural log of both sides. When in doubt, take the natural log. So I have the natural log of 8 times 3 to the power of x equals the natural log of 4 to the power of x. And then since I have multiplication inside of my natural log, I can go ahead and rewrite this as addition. And then I have natural log of 8 plus natural log of 3 to the x equals the natural log of 4 to the power of x. And then now I can bring my exponents in front. So I have the natural log of 8 plus x times the natural log of 3 equals x times the natural log of 4. Then I'll go ahead and collect my x's on that right-hand side, subtracting that x natural log of 3 from both sides to get that the natural log of 8 equals x times the natural log of 4 minus x times the natural log of 3. And now I can go ahead and factor out an x from that right-hand side. to get x times natural log of 4 minus natural log of 3. And then since I have two logs being subtracted, I can go ahead and rewrite this as one division inside the argument of my natural log. So this will be x times natural log of 4/3. And my last step to solve for x is to divide both sides by natural log of 4/3. And so then we get that x equals the natural log of 8 over the natural log of 4/3. And this is approximately equal to 7.23. Okay, great. Right, and then for 10b, I'm going to do something similar. I'm going to take the natural log of both sides to start out. You could do this with common logs if you'd like. The process is virtually the same. So I'll have the natural log of 10 to the power of 2x plus 5, and that equals the natural log of e to the power of 7x plus 3. Now I have exponents in my natural log, so I can go ahead and bring those out front. So I have 2x plus 5. Don't forget to put parentheses around that to remind yourself to distribute that to the natural log. And this is going to equal 7x plus 3 times the natural log of e. But then the natural log of e, that is just equivalent to 1. So that's great. Now I'll go ahead and distribute my 2x and my 5 to my natural log of 10. So I'll get 2x natural log of 10 plus 5 natural log of 10 equals 7x plus 3. And now I just need to collect my x's on one side, so I'll go ahead and move the 7x over and the 5 natural log of 10 over, so I get 2x natural log of 10 minus 7x is going to equal 3 minus 5 times natural log of 10. Now I can go ahead and factor out an x out of that left-hand side to get x times 2 natural log of 10 minus 7. This is, of course, still going to equal that right-hand side. And then my very last step is to divide both sides by 2 times natural log of 10 minus 7 to solve for x. Okay. And this is approximately equal to 3.55 if you were to punch it in the calculator. And that is our answer. Okay, and then lastly we have 21c. So we have two logs being added together, so we can go ahead and rewrite that as multiplication inside the argument of the log. So I'll have the log of x minus 3 times x plus 3, and this is all going to be equal to 2. And now I have a common logarithm because the log base isn't specified. So to get rid of it, I'm just going to go ahead and raise both sides to the power of 10. Right, so then I have x minus 3 times x plus 3 on the left-hand side, and I have 10 to the power of 2 on the right-hand side. So now if I multiply this left-hand side out, I should get x squared minus 9, since this is a difference of squares, and that's going to be equal to 100 once I square that 10. So then I know x squared equals 109, or that x equals plus or minus the square root of 109. And then I need to double check that I don't have any extraneous solutions, because negatives can cause problems in my natural logs, or excuse me, in my common logs. And so then I kind of check if I do the log of square root negative square root 109 minus 3, that's going to be the log of a negative number, and that is not okay. So I think our extraneous solution will be this negative 109, and we know for certain that x can only equal this positive 109. And we can also plug those in to the input of either arguments to see that it does in fact hold. Yeah, that's it. Okay, so let's look at 22a, and we are supposing that it takes a radioactive substance 36 years to decrease by 25%. In other words, 75% of the substance would remain, and we're assuming that there were 50 milligrams initially. So I think my formula generally would look like y equals 50 e to the kt, and then I need to find 75% of 50, so I can compute that. and that should give me 37.5. Since we're decreasing by 25%, we should only have 75% remaining. So then I can set 37.5 equal to 50e to the k, and that takes 36 years to decrease by 25%, so I'll put 36 in for t. And now we just need to solve for k. So our first step would be to divide both sides by 50. And then we get 0.75 equals e to the 36k. And then to get rid of the e, I just need to take the natural log of both sides. So I get natural log of 0.75 equals natural log of e to the 36k. And then since I have an exponent in my natural log, I can go ahead and bring that out front. So I have the natural log of 0.75 equals 36k times natural log of e. And of course, the natural log of e is just equal to 1. So now I just need to divide both sides of my equation by 36. And I get that k is exactly equal to the natural log of 0.75 divided by 36, and is approximately equal to negative 0.00799. So then our model should be y equals 50 times e to the negative 0.00799 to the t. Okay, great. Okay, so now for part B, we need to find how long it will take for the same substance to decrease to 25% of its original mass. Okay, so I think our first step would be to find 25% of that original mass, or 25% of 50. That should give us 12.5. And so now we want to set 12.5 equal to our 50 e to the negative 0.00799t. And we want to find the t for which this equation remains true. So we'll start by dividing both sides by 50. That'll give us 0.25 equals e to the negative 0.00799t. Then we just need to take the natural log of both sides. And then the natural log allows me to bring that exponent down, so I'll just go ahead and do that. 9t times the natural log of e, and of course the natural log of e is just equal to 1. So then our last step is to divide both sides by this negative 0.00799. Just find what t is. And we get that t is going to be approximately equal to 17.35 years. Okay, now we're going to talk about turtles. We're given a population p of turtles modeled by the function p of t equals 175 times e to the power of 0.05t, where t is the number of years since 2018. And then a scientist counted 250 turtles, and so we want to know how long it took to grow that population. So I'll go ahead and set 250 equal to 175 e to the 0.045t, since this p of t equals my output. So I'll go ahead and divide by 175 on both sides. And then 250 over 175 simplifies to 10 sevenths. So we have 10 sevenths equals e to the power of 0.045t. And then we just need to take the natural log of both sides. So we get natural log of 10 sevenths equals 0.045t, natural log of e. Again, that exponent allows me, the natural log of the exponent allows me to bring that in front. Of course, the natural log of e is just equal to 1, so our last step is to divide by 0.045 on both sides. To get that t is exactly equal to the natural log of 10 sevenths over 0.045, and is approximately equal to 173.5 years. Great. Okay, and then for 23b, we want to find the percentage that the population should increase in a decade. So I'm just going to find the percent change from 10 years to 0 years, our initial value. And remember that our initial value when we plug in t equals 0 should just be 175. Okay, so I will just go ahead and compute the number of turtles after a decade. That should be 175 e to the 0.045 times 10. And then I want to subtract my initial value and then divide by my initial value. Remember that this is the percent change formula is new minus old over old times 100, so that's what I'm using here. Okay, great. So then when we punch that into our calculator, we should get that the population increases by about 56.83% in 10 years. Next, I'm going to look at 24. We need to find a formula for the quadratic function with zeros at -2 and 5, and that also passes through the point -1, 8. So I know that my quadratic will generally be of the form y equals a times x plus 2x minus 5, since those are my zeros. And so we just need to find out what this coefficient a is in front. And so how could I do that? Well, I know that this function needs to pass through the point -1, 8, so I'll go ahead and plug that point into in for y and x here. So I'll have 8 equals a times -1 plus 2 times -1 minus 5. So I have 8 equals a times 1 times -6. So then I should get that 8 equals -6a, or that a equals 8 divided by -6, and this is the same as saying a is equal to -4 divided by 3. So then we know that the formula for our quadratic function will look like y equals -4 thirds times x plus 2x minus 5. Great.